All right. Good afternoon, everybody. So this is going to be my second attempt doing it the online classroom, and I'm super excited because we're going to learn a little bit about simple machines. I think all of you are actually from Principles of Engineering Design, where we actually go over all this stuff. So all of this stuff should be a little bit of review slash some of you, I'm sure, aren't 100% sure about everything that we've talked about so far. So today's lesson, obviously, we're going to have the established goal of demonstrate an ability to identify, formulate, and solve engineering problems. And is there a way, can I get hey, Doug, can you actually read the essential question to me? You might have to turn on your audio for this.
The essential question is to describe one situation in which an engineer would want to include a mechanism with a mechanical advantage greater than 1, and what is the advantage in this case?
Awesome. So just so that we're all on the same page, what if you can hear me right now and you were able to just hear what Doug just said? If you in the chat just give me a nice thumbs up. There's a little emoji next to the chat. Just give me the thumbs up. All right, so we got Jackson, Jordan, Maddie, Doug, Tyler. Awesome. All right, so we're going to mute some people here so that echo doesn't happen again. All right, so awesome. So just like every day, we're going to start today's lesson with a nice warm-up. What I want you to do right now, just individually take like half a second, think of what the 6 simple machines are. I know some of you have pretty much, we went over this earlier today, so just think what they are. And I'm going to put you into breakout groups, and you'll be partnered up with somebody else online. You'll be able to use a video chat for this. And I want you to think of like 2 examples from each of those simple machines. Okay, so if for a lever, you're going to think of 2 things that we use every day in the world that uses a lever. I then want you to think of 2 things that we use every day that uses a wheel and axle. Then we can go and do some other of the simple machines. So I'm going to put you into those breakout groups right about now. All right, are there any questions before we get started? You can just write in chat if you're confused. No? All right, so I'm going to throw you into some groups then. So I'll give you about a good minute or so to get this all done. Yeah. All right, I'll give you another maybe 15 seconds. All right, I'm going to bring you guys all back, and we're going to have a nice clear whiteboard. Now, please don't write it on the whiteboard unless I call on you, okay? So let's first start with the 6 simple machines. What I would like, Tyler, can you write one of the 6 simple machines on the whiteboard? Awesome, so he has the lever. Amanda, can you do the second one? Jordan, you'll be right after her. And then Jackson, how about you do one? So we have the lever, we have the wedge, inclined plane. How about we get another one from Jay? And how about Justin? You throw one up as well. No, Matt. So Maddie just asked, is it incorrect if we use inclined plane versus inclined plane? No, I'll accept either of those. Okay, I just won't accept just a ramp. All right, so we have 1, 2, 3, 4, 5 things written up on the board. How about we get one more from Maddie? How about you write one up there? The very last one. And the pulley system. Awesome. Nice job, everybody. So the second part of that warm-up was figuring out what goes into that we use every day as a simple machine. So what I want for this, I actually want to see your video pop up, and I want to hear your answer. So just in case, how about we mute everybody's mic for right now? And the very first person, what I want is, how about Tyler? How about you turn your video on so we can all see it, and then hopefully and your audio, and give me an example of how about any of them.
Example for a wheel controlling an axle is a steering wheel.
Is a steering wheel? Okay. Okay, I like that answer. Steering wheel. Maddie says that she cannot hear you. Can you hit the audio button as one more time? And really talking to your mic.
Example of a wheel controlling an axle is a steering
wheel. For whatever reason, I can't hear you either this time. All right. How about we get Jay? Can you do the same thing?
A seesaw for first class lever.
A seesaw for the first class lever. Nice job. Okay, I like that one. Justin, how about you give me one?
Mr. Haney, we can't hear you anymore.
Thank you for that. Now can everybody hear me? Give me the thumbs up if you can hear me in chat. Awesome. 1, 2, 3. Okay, so we got everybody now. All right, so that will complete the warm-up. Look at all those faces. Now let's get to the actual lesson itself. Let's do a little bit of review, and we'll talk about moment calculations. All right, so we obviously have been talking about simple machines for a little bit of time now. We just went over the lever, the wheel and axle, the pulley system, the inclined plane, the wedge, and the screw. We named a few of those, how we see them every day in our world. Can Jordan, on your mic, are you able to tell me what is mechanical advantage? In your own words, what would you say mechanical advantage is?
Mechanical advantage is how easy something is to move something else with less effort than usual.
I really like that answer, Jordan. Nice job. Just so that there's not too much of an echo, make sure that your mics are off right now at this point. There we go. Because I know, there, Cool. Now we don't have that echo going on. So nice job, Jordan. Jordan said that how much easier it is to move things, move objects. Okay, Tyler, you putting your mic back on. I know that there was some issues with that. Maybe it'll work this time. What is the difference between ideal mechanical advantage and actual mechanical advantage?
Actual mechanical advantage is the exact number, and ideal is close.
All right, I also like that answer. Jackson, can you give me what's another difference between ideal mechanical advantage and actual mechanical advantage?
Ideal mechanical advantage does not involve friction, while actual mechanical advantage does. Take the mic off.
Right, obviously, we have gone over actual mechanical advantage and ideal mechanical advantage. I like those answers from both of you. Now, we did talk about rotational equilibrium and what a moment is. Remember that a moment equals a distance times a force. And when we talk about rotational equilibrium, a moment needs to equal a moment. So what I'm going to do real quick is I'm going to throw on a example of a static or a rotational equilibrium equation onto the whiteboard, and I want you to look at it in your head without writing it on the whiteboard. I want you to try to solve it. In chat, what I would like you to do is, what is this symbol right here that I just drew in my lever calculation? What is that? Nice job, everybody. All right, if I am trying to pull down on this lever, and that's going to be, I'm going to draw a nice little me here. What I would like you to do is, this is in rotational equilibrium right now, I would like you to solve for the resistance force. It just in your head. Give you about 10-15 seconds. You don't need to write in chat. All right. Since Jackson went ahead and started writing it in, how about Jackson? Why don't you take over? I'm going to give you the microphone and give you the pencil, and I want you to show me every single step of this equation.
Where's the pencil at? Do you click it?
Write it. Right. And Jackson, I want you to walk us through exactly what you're doing and why you're doing it.
Alright, so first I multiplied the 15 pounds of force that you applied to the 10 inches, I'm guessing, that there was between you and the fulcrum, because that was on one side of the fulcrum, and then the other side is 12 equal to times x, which we're trying to solve. So I multiplied 15 times 10 and got 150. And then what we learned in algebra was to divide 12 out of x. then that leaves me with 12.5 equals x.
All right, nice job, Jackson. Okay, so that is how we did it. Just so I can show you right here, right now, because this will be the very last problem that we go over. On this side, we have the effort, and on this side, we are dealing with the resistance, because this is a first-class lever. So we know, because previously, and I'm just going to write this onto the side here, a moment equals, what does a moment equal? I want you in chat, write down the equation for a moment. Awesome. So I see everybody is saying a moment equals force times distance, and obviously if it's in static equilibrium, we know that the moment of the resistance has to equal the moment of the effort. All right, and just like Jackson previously stated and shown his work onto the side, we're able to get the answer of 12.15. All right, nice job, everybody. Great work today. I'll catch you all hopefully tomorrow. All right, thank you. Goodbye.